Okay, welcome. Just a small sound check. Just a moment. Nice. I think we're here. I hope we're here. Maybe what I can do is just add it here to periodically check. Yeah, nice. Also, I'm gonna be watching the chat from my phone because, yeah, it eventually happened. It's warm enough. We're at Microsoft Terrace. So, yeah, for those who are new to stream, yeah, for the people who just got to the stream, yeah, we are streaming weekly. Every Sunday or Saturday we are doing LeetCode and system design preparation, getting our skill back. And yeah, usually I'm streaming from the Microsoft Office, but now we are on top of the Microsoft Office on the terrace, and this was my dream since, I don't know, 4 months ago. I wanted to stream exactly from the terrace because this is very beautiful view. Yeah, and overall vibe should be awesome. So yeah, but the stream structure would be actually exactly the same. So first, our agenda is to do LeetCode for a bit. We're gonna do tasks and problems for the priority queue and I think binary search. So priority queue and binary search. Then we're gonna do system design web crawling or web crawler. And that will be it for the agenda today. We're not gonna stream for a long because sun is going to be off soon. So let's just start right now. So yeah, any questions or anything you want to share or to tell me, just go for it. I'm tracking the chat. Everything is on track. So, yep, we have our task, total cost to hire K workers. So let's just go through it. If there is any problem with sound or you hear the music too loud or I'm not loud enough, just let me know also. So we are given zero index integer array costs, where cost I is the cost of hiring the ith worker. And we're gonna run K sessions to hire exactly one worker in each session. So we're gonna have probably some K iterations, and we are going to do something with one worker in each session, and this is strict rule. In each hiring session, choose the worker with the lowest cost from either the first candidate's workers or the last candidate's workers. Break the tie by the smallest index. So yeah, I will run an example later. Hi, do you know when the below senior positions will be open in Prague? I guess. Sorry, let me check the nick. Look, my fuck. I guess you just pasted some link or I don't know. Anyway, I actually don't know anything about open positions in Prague. I only know about open position in my team, and I know that for the last 2 years we don't hire externally. We only some periods of the year, for a couple of months we were hiring internally, and now I think both hirings are closed for my specific team. For globally, for the Prague office, I have no idea how it's going. I have no idea even when and how to apply, to be honest. So I'm sorry, I don't think I can help with this. But in general, the situation on the market right now is very bad, especially, yeah, most probably you knew already is that Microsoft laid off a lot of people. Also, I knew a bunch of people, I think around 10 in the Prague office that got laid off as well. And yeah, so I don't think like there is big demand in the IT engineers or software engineers right now. So when the below senior positions will be open, when I have no idea when. Sorry mate, I have no idea. So yeah, good. Yeah, so back to our question. In the second hiring session, we will choose first worker because they have the same lowest cost candidates. So we have the array, let's say this array, and we have candidates equals 2, which basically means, and let me draw it as well, which basically means that if we have candidates 2, it means we are taking 2 candidates from the start and 2 candidates from the end of the array, which is stated right here. So it means what we're gonna choose from these 2 workers and these 2 workers, because candidates count is 2. And we're gonna choose the lowest cost among these 2 lists or whatever. And if they are same, so let's say first we chose 1, it's done. We should move our array to the next element from the right, because we just removed 1 element and we still should maintain this candidate's number according to our invariant. And now we have 7, 2 and 3, 2. Apparently the lowest element in both of these arrays is 2, but it's tie. So which one to choose? We should choose the one with the lowest index. So if there is same value, we basically choose from this list. We again expanded because we should try to keep our candidate count 2. And now, how many workers we should do? We should calculate k, and k in this case is not stated, right? So let's say if we need to calculate cost of hiring 2 workers, we already did it. It will be 3 because 1 plus 2 is going to be 3. If we need more workers, let's say k equals to 3 or k equals to 4, let's run it through. The next element among these 2 lists is going to be 2 because this is the lowest. We add in 2 as well. Now it's 5. And we don't have anything to expand because list is already exhausted. So we will just keep the right array with the number of candidates equals to 1. The next element is going to be 3 for sure. Now cost is going to be 3. And then we have tie, we choose first from the left, it's going to be 7, and then we choose from the right, it's going to be 7 as well. And we run through all of our list, we don't have anything else to process, we should return the cost. So this is going to be the problem. We should return the total cost to hire exactly k workers. So we basically have 2 lists from the left, from the right. We should, every single iteration until we hired k workers, for every single worker we should choose the lowest cost among these 2 lists. And then we should try to keep lists of the same size if we can. If we cannot, well, it is what it is. And yeah, in the end, when we hired k workers, we should just return the cost. So since this is the topic of priority queue, which is already a huge hint, in general, in interview, you won't have it, but if you want to keep some array and you want to have pretty good constraints and time complexity for adding to this array and popping the smallest element every single time. So how you can do it? In general, you can have it just with a single array. And then you can sort array every single time you add element to the end or you remove element from the end. So removing and adding element to the end is going to be constant, and sorting is going to be n log n. Instead, what you can do, you can use heap, which provides you with much better complexity. So every single insertion is going to be log n complexity, and popping is going to be log n complexity as well. So you're just eliminating n in this case, which is we going to use as well. So what is about the algorithm? So we're gonna just get the right heap with the candidate's number of elements in it left with the same number of elements And then we just start our processing until we exhaust k. We're gonna proceed. Once we remove element from left heap, we try to push and expand this heap if it is existing, because the thing is, what we don't want to have actually, or I think even this example is very representative in this case. What we don't have to have is exactly this. So we have 3 candidates, and 3 candidates means that this is going to be our right heap, and this is going to be our left heap. And this is something what we don't want to do actually, because we're going to have overlapping in this case. And if we just keep it as is, so our heaps are overlapping, we're going to process duplicate values, which you don't want to do. So what we're going to do with this is actually we're going to perform some invariant or algorithm that keeps invariant that left heap is always or I mean in other case that left pointer, the left tail pointer in this case, which is going to be this one, it never can be pointing to element that is tail pointer on the right heap. So I think you got the idea. So once, let's name it L. L is the last pointer of the left heap, and right is last pointer of the right heap. So we keep environment that left is always less than right. So let's just basically start. Yeah, look, yeah, thanks. No problem. Sorry, man. I really don't know anything about hiring in Prague. Only in scope of my team, I can tell you something. Yeah. Good. So, how we're gonna proceed? Let's just paste it here. I'm completely on my laptop, so I even don't have my keyboard and mouse. Or I mean, I have mouse, but it's a pretty shitty one. So I'm gonna use vMotions for sure in this case, 100%. So okay, what we want to do, let's define left heap as array, right heap as array as well. And what we want to do, we want to populate them. So maybe let's even try with the left heap straight away. So how we're gonna proceed? While, yeah. It's going to be our left index, which we start from the 0. And while left index less than length costs, or we do have constraint that it cannot be bigger. So, no. Oh my God, what I'm talking about, it should be always like this. So, how do we proceed? We just keep the, and our candidate is at least 1, so we for sure gonna enter this array 100%. So what we are doing, we are adding it to our heap q, heap push, I guess, left heap, and we are pushing costs left index. Oh no, this is not what I wanted to do. And now, if our left index plus 1 is equals to candidates, we just break. Otherwise, left index is going to be plus 1. Why so? Because let's say in this example that we have 1, 2, 4, 1. This is going to be our indices. Okay, candidates is going to be 3. So we start our left index here. We are pushing our element, moving it to the right. Yeah, 0 plus 1 on the first iteration, 0 plus 1 is not equal to 3. Now its index is 1. 1 plus 1 is not equal to 3. We're moving it ahead. We are adding element 4. Now index 2 plus 1 equals to candidate 3, and this is when we stop. So this is when we're gonna stop, and the rest is left for the right heap. So our left and right indices are going to be exclusive in this regard for our heap. So that's it. I guess now we can do for the right heap pretty similar stuff. so right index, but it starts with the length costs -1, and we are starting while right index more than equal or 0, and also what we want to do that right index is greater than left index, because we don't want them to overlap, otherwise algorithm will be broken. And now pretty similar stuff should happen here, except couple things. So we are pushing to the right heap and to the right in this index. Now, how are we gonna get the length of candidates? So I think count equals length costs minus right index. I think this is gonna be our number of candidates we have so far. So let's just basically check it. Right in minus. So in this exact example, we are starting with index 3. 3 more than 0, yes. 3 more than 2, yes. We are adding it. Now length 4 minus right index 3 is going to be 1. 1 equals to candidates. Actually, no, it's not. So if 1 not equals to candidates, we don't break. Right index minus, and we break on this clause here, because right index is going to be 2 right now, and 2 is not bigger than left index. What if we don't have left index here and have it here? Then in this case, we again on this position, our right index is going to be here now, and let's say candidate is 2, just for the sake of example. And now we're gonna have, we are adding it, then 4 minus 2 equals 2. 2 equals candidates, yes, and we're gonna break. Exactly. So this should pretty much exclusively identify right and left heap. Now our algorithm is pretty simple. So yk more than 0, so we have workers 2 higher, and also we should have both heaps not empty. So left heap, len left heap more than 0, and len right heap more than 0. Then we proceed, and how do we do? Okay, our left item is going to be heap q heap pop from the left heap. Our right item is going to be exactly same, but from the right heap. Now, if left less than or equal right, while less than or equal, because in case of tie here, where is this? Yeah, by the smallest index. So if they are equal, we still want to take the left heap because it has a smaller index. So if left is less than or equal to the right, then what we're gonna do? We're gonna, let's also define our cost here. Cost plus equals, oh shit, it shouldn't be heap pop here. I'm sorry for this. Left heap 0, actually it should be, because this should be a pick operation, not a pop. We don't want to remove element until we know we want to process the left heap. So now, yeah, we want to do a heap pop, and yeah, now we lost one of our candidates from our left heap, so we want to repopulate it again, and we are checking if left index plus 1 is not equal right index, and oh my god, and right index. What about right index? Well, we also want left index plus 1 be less than len costs. However, no, we don't need this. We don't need, because right index will guarantee it's less. So yeah, if it's not overlapping, we actually want to add it back. Heap push, left heap costs. Yeah, also left index plus equals 1 and new left index. That will be it. In other case, we are doing exactly the same, but with the right heap. Good, and exactly the same thing we want to do for the right heap. So if right index minus 1 is not equal to left index, we're going to do right index minus 1 and heap q, heap push, right heap, and cost right index. In the end, we want just return cost that we got. Also, one thing here that yeah, one of the heaps can be actually empty. For example, in this specific case, where is it? Where is it? Yeah. So in this case, let's assume we are taking the right guy. So our left heap becomes this, and right heap becomes empty. So we want just to process only the left heap. Let's exactly do this. So if len left heap more than 0, else what we want to do, if we don't want to process left heap, it is empty, we want to process right heap, and in order to make it work, we want to break this if clause by the very high left. If left will be higher than every possible right, we're gonna go here. So I'm putting it 2 to the power of 32 because 10 to the power of 5. What is higher, 10 to the power of 5 or to the power of 32? I somehow assume that 2 to the power of 32. Same thing actually we're gonna do here. If len's right heap more than 0, else 2 to the power of 32. Because yeah, we don't want to process the right, we just should make it high element enough that it will go to this if. Now let's try to run and fix all the bugs. Keep going, bro. Thank you. We keep going. Int list, what do you mean? Int list. Yeah. What the hell is this? Exactly. Index out of range. Okay. So how it can happen? He put list out of range. Most probably left index somehow got out of range. But shouldn't it be guaranteed that right index should be? Somehow we lost right index. I mean, it should actually guarantee that if it's not, then yeah. It's quite interesting how it happened. So let's run it through. Actually, more faster will be print left heap for debugging. Print right heap. I just don't want to waste time. think we just have some stupid error. I don't know. Yeah, out of range. So we have 1 to, yes, exactly. 2 is our index. Well, it should never be equal. How it's 2. Okay, 2 is not expected, I guess. We shouldn't have processed. Okay. So this guy, I think, right index more than 0. Yeah, and if it's more than left, now it's gonna be equal. Yeah, it's actually bad. I will do this, or right index -1 gonna be left. So if it's true, then we should break it. Right. Yeah. Oh my god. Left index. What the hell is this? Okay. Left index and costs. Okay. Okay, this one is interesting one. Let me check. Okay. I see. It just should be also, because we hired one worker, we should not forget to, oh, no. To remove this one worker. Yes, and this fix, and I think this should be done actually. Let's try to submit. this out of range, cost left index. Okay, let's actually do plus 1 less than costs, just to make sure. And right minus 1 more than or equal 0. Yeah. What the hell is this? Wait, let me go through again through this algo. It should actually work. So that index less than costs. Length of cost, yes, we are pushing it. Good, plus 1. Good. Good. I don't know, for me it seems like it shouldn't break at all. Why doesn't it work? I'm wondering what is the error actually. Okay, so we are defining left heap and right heap. Well, yeah, okay. If, yeah, actually should be good. Okay, now I have this piece of bullshit. Zero, 1, 2, 3. Okay, I think I'm getting closer and closer. Let's again troubleshoot a bit. So print left, right, print left heap, right heap. I don't understand why it does, like the algo should be perfectly fine. Yeah, this shouldn't be like that. 2, 2 shouldn't be. How come it became then 2? So I think it's okay, and this one is 3. 3 is more than 3 is more than 2, exactly right. We're adding it. And now 3 minus, no, sorry, 4 minus 3 is going to be 1. 1 is not equals to, how many candidates do we have? 3. So no, right index minus 1. So index becomes, okay. So actually this check is needed here. Interesting. Okay, or what the hell? I'm sorry, but it just didn't work. Both of the test cases, what the hell? Okay, let's try some bit now. Pretty strange, but we got it. Yeah, I have no idea how come. I will rewatch later on, but the algo should be perfectly fine. Anyway, so no more comments, I guess. Yeah, no more comments. Just proceeding. So, what is the time complexity for this algo? So first of all, let's denote C as candidates and K as a K. So first of all, we are pushing candidates and candidates from both ends. So it's going to be candidates times log n, since pushing to the heap is log n. And at this while, in this one, we are doing K times popping from the heap. So plus K, plus K times popping from the heap, which is also log n. This is roughly the time complexity, and space complexity, we are keeping 2 heaps of the size candidates, so space complexity is this. Guess we're done. Thank you for being with me so far. I don't know what happened, but it's very hard. It was very hard to spot the error. I don't know. Yeah. So I think this one we are done with. Now this question. This is actually pretty simple binary search problem. So this is exactly what is binary search is going to do here. This is exactly what we want to do. So guess number higher or lower, we have some function that returns us 3 values, whether this is the number that the programmer or someone guessed, less than that or greater than that. So basically this is just regular binary search, but in order to understand whether our target is less than, equal, or bigger, we're going to use this function. So typical binary search algo works like this. So we have our left pointer to 0. We have our right pointer pointing to n. No, not 0 actually. It's from 1 to n. Now, while left less than or equal to right, we're performing mid, which is going to be left, right minus left divided by 2 to the lowest basically floor function. And then what is going to happen if, yeah, let's do our value or result, I don't know. We're gonna call guess function, which is denoted here. So our guess function with the mid. And now if response -1, your guess is higher than the number I picked. So the number I picked is less than our mid. So if our mid bigger than number we picked, we should go left because it's sorted kinda. So in this case, if res equals -1, we go left, which means right equals mid -1. Else if result equals 1, which means our guess is equal to the number your guess is lower than the number I picked, so number I picked is higher than our mid, which means we should go right. And to go right, we just adjust in the left to mid +1, and else we just return mid because response equals to 0. Yes, and 0 means this is exactly the number we were returning. And just for the to make all branches return the value, we're returning -1, but we should never reach -1 in this case if there is number in this range. Yes, exactly. It is working. Nice. Time complexity log n, because every single time we are narrowing our search space twice. So it's logarithm. Next one, successful pairs of spells and potions. Oh yeah, I remember this one. So we have some spells and potions of length n and m, respectively. Spells I represents the strengths of I spell, and potions represent the strengths of j potions. Okay, integer success, a spell and potion pair is considered successful if the product of their strengths is at least success. Return array pairs lengths n, where pairs I is the number of potions that will form a successful pair of the I spell. So, yeah, this is a bit long and not quite understandable. Let me run the example. So we have 3 spells and some number of potions. In this example, they are already sorted, which is actually the hint in this case. So what should we do? Like the spells is the multiplier. So for the 0 spells, this is the multiplier we're gonna check each potion with. So for 5, we actually multiply every single potion, and this is the value. And what we want to do, we want to count the potions that have value which is greater or equal than success. So in this case, 5 is less than or equal 7, and all of these are bigger or equal to 7. Next, it happens with multiplier 1, because this spell, we do exactly the same, and all of them are less than 7. Same happens with 3, and 6 is less than 7, but 9 is more than or equal to 7. So 3 pairs, and this is how we're going to perform that and return the response. So, yeah, in short, the solution to this problem is pretty simple. The key trick here is to sort potions, because then we can easily find the lower boundary. Well, not easily, but we can find the lower boundary of the. Let me actually put on the jacket because it's quite cold right now. Yeah, so we can pretty easily find the lower bound of these potions, and that will be it. Basically, that will be it. Once we found the lower boundary, let's say we found that lower boundary here is 10, we just take this index and calculate the length of this array. So basically, for every single portion, we need just to find this lower boundary. If the list is already sorted, it's log of n due to a binary search complexity. And then calculating the number of portions is just constant because it's just math. Right, so this should be a pretty yeah, good algo here. So let's define our result. Let's also sort potions. By default, Python sorts potions in ascending order, so from lowest to highest. Now we're gonna traverse all the spells, and here we're gonna perform the binary search. So our left, exactly the same one, but with the one trick I will show you later on. So right, it's gonna be len potions -1, and now while left less than or equal to the right, defining our meat, right minus left divided by 2. Now it's quite interesting thing because we don't have specific target. Why so? Let's say in this specific case, for this spell, we have 2 10s, meaning we have 2 potions equals to 2. It's not constrained, there can be duplicates. So in this case, if we even search for the 10, and let's say somehow our binary search gives us this as a lower bound, it will be not true. So what we should do, we should try to pick the lowest possible boundary, which means our target in this case going to be 7, our success. And we want to find the value which is going to be 7 or bigger. How we can do it? So instead of which, we're gonna have just 2 ifs. So if our value is actually our multiplier times potions mid. This is how we get this specific value already multiplied. So if value, or sorry, if our success less than or just less than or equal, exactly less than or equal to value, if success to the left, basically we again shifting our right to the mid -1, else we are shifting our left mid +1. I will draw the explanation now so you're gonna understand it. Let me also change to lofi hip hop because it's a bit boring already. Exactly. Hope sound is good. Maybe a bit lower actually. So in this case our success is equal to 7, and what we're gonna do here, we're gonna look for the success. So how we're gonna perform? So let's say we somewhere here, our mid is going to be this one. No, let's actually do, this is our mid. So 7 is definitely less than 10. So we're gonna perform check on this, guys. So 5, 10, mid gonna be here, this is right, this is left. Now we clearly understand that 7 is more than 5. So our 7 is more than 5. We go this way, mid +1. So our left becomes here. This disappears and mid becomes as well this one. And now our 10 is actually 7, 7 is less than or equal 10, right? It's definitely true. So we move our right back. So our right becomes here, but left is still the lower boundary. So the trick here that in the end, after this while run, what will happen that our left will be pointing exactly to the lower boundary. So what we just do, we just response append length portions minus left. So in this case, if this is the 0, 1 index, length 1, 2, 3, 4, 5, 6, 6 minus 1 is going to be 5. And 1, 2, 3, 4, 5. This is exactly the number of our portions. And we just appended it, and in the end, we return res. As simple as that. There is all flying, nice. Good. We are done with this. The complexity we are running through all the spells, if it's n, it's going to be n times log m, where m is number of portions. Space complexity going to be log of portions, because sorting might get merge sort or some other thing that will take this memory. If sorting does not take any memory, the space is constant if we don't count the result. If we count the result, the space is number of spells. Good, we are done with this, and now we're gonna perform the escalate draw. Yes. This was my learning for dynamic programming. Look at this beautifulness. Top-down caching drawing here. So yeah. Last time we were designing URL shortener, and let me just check. Yeah, last time we were designing URL shortener and checking the other solutions on YouTube, which were not that satisfying and good. Some of the flaws. So in general, the core idea here is to generate this unique ID generator, because converting unique number to the URL shortener, this short sequence of the characters, is one of the best ideas for this solution. And what you should do is to perform and design scalable unique ID generator, which already has proven by production algorithm called Snowflake ID. And most of the people, I don't know, somehow don't use them, because Snowflake ID algo allows you to implement unique ID generator without any storage, without state, so you just spin a bunch of computes and you're done. But it is what it is. Right now we're gonna perform system design of the web crawler. So let's do it. So typically, web crawler system design requirements. This is what I want to do. So what is our typical requirements? URL discovery. Implement mechanism to discover and enqueue URLs from various sources like sitemap, seed URLs, and discovered links. Content extraction. Okay. Prioritization. Pages based on factors such as relevance, importance, freshness to optimize crawling efficiency. This one actually sounds like a bit of bullshit, because if you can design a system that scales enough, you will not just have any pending URLs, because you can just scale the number of workers and that's it. And that's it. You will, regardless of priority, you will have everything parsed. So I don't really understand the priority thing here anyway. Content types, blah blah, scalability, horizontally, okay, so we're talking about millions of requests, good performance, fetching, robustness, handle errors, maintainability, security. Okay, so pretty typical one. Most probably if you're getting something like that on your interview, what you're gonna get that millions of requests per second. So it means millions of URLs to crawl. Millions of URLs to crawl. Yeah, now what else? Now what else? What else? What else? It's going to be, I mean, pretty scalable, highly available. So highly available. Yeah, from the functional are these these are non-functional requirements. So non-func or fault tolerant. Basically, I think we can assume eventual consistency here because it shouldn't be instant, the crawling. And from the func requirements, so functional requirements, yeah, API for submitting the crawling, basically something like Google Search Console. Explorability. So what do I mean by that? That while we are traveling our HTML page and we are parsing it, we're exploring links and adding them to parse for later as well. Recrawling periodically, and also here what also can be added, omit duplicates. I don't know, something like that we can do for now. So let's start. Basically, what I would start with is our front-end node. So basically, I would write here something like that. It's going to be our front-end API or whatever. Oh my god, I hear that microphone is touching my t-shirt or something, I don't know. So this is our front-end API, and this is completely stateless. Shit. Yeah, group, good. Now this is completely stateless scenes, so we have a bunch of them. Yeah, they are behind some load balancer, whatever. So yes, LB. And what they do, validate and sanitize the URL. Yeah, this guy validates and sanitizes the URL. What does it mean? Because you can parse a lot of URLs with different query parameters and stuff like that. You should remove anchors first of all. So these are the things like that. They should be removed. These are the pointers where page should go. We should reorganize and alphabetically sort the query parameters because we want to run the duplication later on. So we should like two different URLs with different cases. For example, they should be basically case insensitive. So we do it to lover, and we are sorting the query parameters. So in the end, like these two URLs should be the same. However, initially they might not be equal to each other. So this is the responsibility of this guy, and it can do it completely stateless. Now this guy, what we're gonna do the next, since it's going like this, since they scale easily because they're just stateless computes, you can put as many nodes as you want. Also, however, you can put some rate limiter here as well. Just rate limiter or whatever. Now, what is going to happen here? We have load balancer here as well, but this is our internal load balancer, and it works. It balances, basically it works more like partitions by hash URL. This is what this guy is doing. So it takes the URL, it computes the hash, and based on this hash, it decides to which partition it will go the next. So in our case, we would have a bunch of partitions. what every partition is going to have, it's going to have the backend node. However, this node is actually backend as well. It doesn't do any HTML serving, but it's kind of internal frontend or internal frontend, whatever, or let's name it internal backend. And this guy, let's name it backend. Exactly. So this is internal backend node right here. This guy is also stateless, so we can spin as many of them as possible. And now, like, this is already a sanitized URL, so this is completely URL that we can work with to crawl. But this guy will not perform the crawling. This guy, what it's going to do? It's going to go to cache. Yes, so cache. This is some URL. Info, whatever, also grouped. So what it's going to have, it's going to have URL, it's going to have parsed datetime, and might be priority, but actually 2 of these fields should be enough. So why I do have this thing? First of all, that parsed datetime and in general existing of this of URL in this cache signalizes that it got visited. But what another functional requirement we should perform here is that we can actually revisit the nodes, because, for example, let's say you crawled my website, I don't know. And actually, after half a year, I changed the content of this article, which means that actually what you're gonna show in your search result is not accurate anymore, because you're gonna show the result based off relevance, of description, of the content of this article, and it can be, I don't know, my OnlyFans at this point, at this page, right? So you should actually recrawl this URL periodically. So for that, we're gonna have some, we're gonna have some scheduler actually, and for that we need parse datetime, because let's say we can set the policy to recrawl every page every single month, right? And in this case, how you would understand that page should be crawled or not, you're just checking that this parse time, current time minus parse time, is more than or equal than months. In this case, you proceed. Otherwise, you just keep it as just visit, because if another node already took this URL and our parse datetime would be like 2 minutes ago, and we should just skip in this case. So we're checking. So here in this case, check last parsed one month ago plus. So this is what this guy going to do. Good. And if it's good, if it's already parsed like 2 minutes ago, we just skip. Otherwise, we are injecting our job, which is basically the URL itself, to somehow of queue, some kind of queue. It can be a different queue, because like in this case, we should not worry about the load, because I'm assuming that we're gonna partition to kind of deployment unit, which gonna include like database and compute and all of these. And all of these guys, they gonna perform and process only the URLs that by hash got load balanced to this thing, right? So in this case, we can just spin more of such deployments, and it's going to be performed as a consistent hashing manner. So in case we need to add some node, what we're gonna do, we're gonna just shift a bit of data from this database and data from this queue, and just introduce the new deployment unit, kind of. So yeah, consistent or rendezvous hashing should be good here. Consistent hashing. Consistent hashing has some problems as well, but let's say it's okay at the moment. So yeah, this is going to be some queue, can be Kafka, can be actually even Rabbit in this case, but Kafka might be better in terms of oh, hello. Is that real background? Oh, sorry, I missed the message completely. Yes, this is the real background. I don't know how to show you. This is my terrace of Microsoft Office. Yeah, we are streaming from here. This is completely real background. Now I should adjust it. Yeah, should be quite good. Yeah, something like that. I can move. Nice, looks good. Thank you for commenting. Yeah, so now we are injecting this URL into the queue, and for the queue, the queue is going to be read by a bunch of workers. So we're gonna have worker 1, worker 2. These are also completely stateless computes, so they are not storages. And now this worker actually going to perform parsing of the page. So it goes, checks robots.txt, tries to parse the content, generates the hash of the content, stores it somewhere. So this guy actually going to store also the crawled information in some big storage, which is not actually covered in our case. So this is crawled index or whatever. Crawled index. It is going to just push the HTML content somewhere here, and it will be indexed by some other entities later on, right? So yeah, that is the plan. Yeah, and it goes to the website, checks it, and also updates the cache, the last parse time. In this case, yeah, we can process actually duplicate. So I mean, the same URL can be processed twice, because yeah, in this case it's at least one guarantee. I don't think we can actually ensure properly and with the low cost the guarantee that URL will be parsed only one single time, because overall nothing bad happens if we process the URL twice, only that we will use the compute capacity, but it's not something bad. So we don't need even to guarantee here. Just try to be as optimistic as possible with this parsed data. Yes. Oh, sorry, again this micro bullshit. I hear it. That would be it, and this is, yeah, the queue can be actually also has some property of scaling and replication. Yeah, now for the fault tolerance. For all the compute nodes, like workers and internal backend node, we can easily add new nodes without any problem at this point. So you can deploy spin new node and it will just start working. So you're subscribing to the queue and stuff like that. So this is not something that we should worry. What about the database? Yeah, database might be, or it's caching actually. We don't need, or it can be actually database, but for quicker access we can have, like, we can put Redis and use it as a storage or something like that. Because yeah, anyway, if we lose link, so link was parsed months ago or more, we can basically assume that it is already outdated, and we can actually even remove. So we can even put the invariant or expiration for each row in this database, let's say in cache, that after 1 month the key is going to expire. Yeah, for fault tolerance we're gonna have a bunch of followers here. Mostly what we're gonna do, we're gonna read the value from here, because mostly even for duplicates we're gonna reach the same URL, and check the parse date time, and I guess for most of the time it will be less than 1 month ago. So these are the followers. In case our master cannot catch up with the number of updates and writes, what we can do, we can basically scale whole our deployment. So we're going to introduce another deployment and add it to our load balancer. So, and by scaling it, what I mean, we can just split the database by 2, split the queue by 2, and perform something like consistent hashing. So we just reshuffle, you know, this environment that if we have n of all data and we have m nodes, we're going to reshuffle only n divided by m nodes or data items. So yeah, I think that will be it. We can play actually a bit more because most probably the load on the queue and database can be different. It can be different, but yeah, in general, what I like about this system design specifically, that once you have URL, this URL cannot go to any other deployment unit in this case. So we can only face some concurrency issue inside this guy. And if we have, for example, just single backend here, it will be all right. However, we can even scale, put some load balancer inside it, so we can kind of scale this subsystem here individually. So put more internal backends, scale the queue by partitions, partition the database even more, and independently partition the worker. It's workers. It's not a problem as well. So we can do that as well without any problem. But in this case, the partition, well, we can use same URL hash as a partition key, but it will be less nodes and it will be operating over this. But I like the idea that it will be quite isolated. And still we don't lose any properties of our scaling or fault tolerance, because this thing can be replicated on its own. So millions of requests per second quite easily can be satisfied. Fault tolerant, yes. Eventual consistency, yes, we can wait. I mean, if queue is overloaded, it has a lot of data because we don't have workers, we can work on this. Anyway, we're first gonna save the record here, URL information. We can have some even maybe exclusive parsing flag. That would mean that, okay, currently this URL is processed by some of the workers, so don't touch it. Also, there's going to be some scheduling job, but this is completely separate system design. So it should be separate system design question to design a scheduler. So every single time we process the URL successfully and we are adding it to, we are updating this record about the parsed URL, what should happen that we are scheduling the job to revisit this URL in 1 month. And for this, we need to design a separate scheduler over there. That would be it. I think that this is our system design. I guess it should be quite workable at this point. Maybe I will try to check the information. Is it good enough or not? Let's actually see. And I think that's it. That's it. Redis or Docker? Well, I guess it's Redis. Docker is the containerization technology. So most probably everything here should be in Docker. At least computes are going to be put in Docker. Whether to put storages and queues in Docker, this is, yeah, a lot of debates are over it. Because, for example, my tech lead, which I guess one of the smartest people I have ever met, sorry, system design. Yeah. He's for Docker for everything. So even storages, databases, queues, they should be in Docker. You have a clear mechanism of volumes to preserving the information on disk, so there should be no problem. And overhead of containerization is actually not that big in terms of trade-off for containerization, isolation, and stuff like that. So he's for Docker, so you can put. Actually, for my startups, I'm putting to Docker everything, because then, yeah, I'm using virtual machines. If I need to move everything to another virtual machine, I'm just copy pasting my Docker Compose, logging into my container registry, Docker Compose up, and everything is working. I just need to maybe migrate the backup of database, and that's it. So easily to replicate the environment. And locally it works the same, so easily to replicate. I guess this will be it. Yeah, if any more questions, I actually don't see any more questions at the moment. So yeah, I think we're gonna close the stream soon. Yeah, it was me, Andriy. We are here at on the terrace at Microsoft. Maybe we will revise the system design a bit later, because maybe I will find some flaws in it. Maybe some improvements can be done in this case. But let's see. For now, it was me, Andriy, with you. Thank you for being with me here, and see you next week. Bye-bye.